Swayam Prabha. Digital India. Educated India.
Hello, we will continue our discussions on Gromacs simulations. So last time we did the simulation for water, we did the distribution functions as well as the diffusion constant. Now we want to extend this approach to mixture of two solvents. In this case what we are taking, water and methanol. So all this discussion is for this mixture, and we will continue with this discussion. Okay, start with the file structure now.
Yeah, so to perform molecular dynamic simulation of water methanol mixture, we need first of all we need the PDB file or the structure file for water. We will also need the structure file of methanol, which is meoh.pdb. Then we will need the topology file for which will contain the force field parameter of water as well as methanol, and we will need molecular dynamics parameter file, that is the MDP file for energy minimization as well as full molecular dynamics simulation.
Yeah, so before we proceed, we have to first decide what composition we want.
Yeah.
So we have chosen a 50%.
50%.
Okay.
Here also the initial configuration is generated using the software PackMol. So just open the file water.pdb and meoh.pdb using the command vi. So vi water.pdb and vi meoh.pdb. So water structure I have already discussed earlier, that water, like the last three columns represent the coordinates of oxygen, hydrogen and 2 hydrogen in XYZ axis. Then SOL is a residue name, then there is bond connectivity and angle connectivity. And this is the PDB file for methanol, where we have taken methyl group as united atom, like we have taken methyl as one group, and then there is oxygen and hydrogen. So, and the residue name of methanol is MEO, and this is the coordinate of XYZ axis, and connect 1 3 and 2 1, which means that the bonds are connected, like O1 is connected to methyl and O1 is connected to hydrogen, and connect 3 1 2 is the angle connectivity.
So now those on the extreme right are the coordinates of oxygen,
methyl
group
and hydrogen.
Yes. Again in angstrom units.
Again, yeah, it is in angstrom since it's a PDB file.
Okay. So 1 and 3 are connected and
2 and 1 are connected.
So instead of 2 and 1, can I give 1 and 2?
But just a sec, 1 and 3.
Yeah.
And you want to give 2 and
1 and 2.
Yeah, 1 and 2 is fine, because anyways O and H and O connected.
Okay.
So you can as well give 2 and
instead of 1 3, I can give 3 1.
Yeah, not an issue.
And instead of 3 1 2, can I give 2 1 3?
Yeah, you can give 2 1 3.
Okay.
CH3OH, yeah, you can give as well that.
Okay. And again the bond angle can be calculated using vectors.
Yeah.
And bond length can be calculated just by distance between two sides.
Two sides, yeah.
Okay.
So now since we have PDB file, so we have to specify what numbers we are going to take and what is the box length we are going to take in the INP file, which is the input file in PackMol. So this is the INP file name is water meoh.inp. So if one wants to download an INP file or wants to see what an INP file for a mixture looks like, one can go to the site PackMol, and there they will have water urea INP file, which is a binary mixture of water and urea. In an input example, they will have the file, they can download the INP file, they can download the PDB file of water and urea as well.
But can we not take the INP files for the two and create for the mixture?
It's the same thing actually. So I'll just show you the INP file.
Okay.
So this is the INP file for water methanol mixture.
Okay.
Whatever we have taken in case of water, right? We have taken water, structure, number, inside cube and end structure. We just have to repeat this 4 line for methanol also, because methanol is also being added to the mixture. So we just have to add this 4 line for methanol. You change the name of the output file. You just have to add structure meoh.pdb, which is the PDB file of methanol. You have to specify the number, what is the number that you are going to take, and the box length.
Can the order be changed?
Yeah, the order can be changed.
Instead of meos.pdb first and those lines?
Yeah, the order can be changed. The order can be changed.
Okay.
Not an issue. So again,
and why have you called it water meoh50.pdb?
Because this is the water methanol mixture and 50% mixture. So to have a clear idea, suppose you are doing more and more simulations, so you have many output file. So you'll have a clarity.
So it is good to have a file name which reflects the final composition or the initial composition.
So that you won't get confused. So this is the output file name, water meoh50.pdb, and 30 is a cubical box of box length 30 angstrom. So it is designated as inside cube.
Okay.
So now we'll execute packmol using this INP file, and we'll use the same command /packmol less than water meoh.inp. So after the successful execution, we'll have something like this displayed in the screen, like solution is written to file water meoh.pdb, and then what is the time it has taken to complete it. Right. So now we have the PDB file. So now we'll create what mixture.pdb mixture directory or mixture 50 or water methanol mixture directory in the working directory, in the Gromacs directory, and then we'll copy the file water meoh50.pdb to that directory, so that we can convert it into a GRO file and we can proceed towards the simulation.
Okay.
So now we'll convert the liquid water.pdb file, or water methanol 50.pdb file to conf.gro file.
Okay.
So we'll first copy this file. So to copy, we'll have to type the command cp.
So you have first already make directory mixture 50. You have done that, and then copy to that directory.
Yeah.
Again, there should be space between the two dots.
Yeah.
Okay.
So now the file will be copied, and now to convert this PDB file into a GRO file, we'll use the command genbox. So genbox space minus cp, which is a flag for input file water methanol 50.pdb, then space minus o, which is for output, space conf.gro, which is my output file, then space minus box, and after that we have to give the box length in nanometer, which is 333. It is a cubical box of 3 nanometer, and then we type enter, and after that something like this will be displayed. So it will read the solute configuration, which is built with packmol. So there are total 2586 atom and 862 residues, because there is 431 water and 431 methanol molecules, so total 862, and then it will show the volume, density, number of solvent molecules.
So this density is the total density?
Total density of the mixture.
Okay, that is the volume. So it is saying number of solvent molecules 431.
Yeah.
Now suppose you did not have a 50-50.
Yeah.
Then will it show two numbers there?
Yeah, it will show two numbers there.
Or it will show one of them, because the
other one is self-understood at what will be the other one. Yeah.
So now that there are 862 molecules, this was not predetermined.
Yeah, this was predetermined, because you will have a density of water methanol mixture,
okay,
right? You know the density of what is 50% mixture density. From that density, you will calculate the number of molecules for water and for methanol.
So that
246.73.
What is the unit there?
Grams per liter.
Okay, so this density you got it from experimental density?
Yeah, this is the experimental density
of the mixture.
Yeah.
Okay. But one thing I want to tell all the learners is that when we calculate these densities, does it worry about the partial molar volume and things like that, or it is just a numerical calculation?
When we calculate the number of molecules?
Right, because see, when you mix water and methanol,
yeah,
the total volume is not the sum of volumes.
No.
Right. So this is really a rather complex issue. So what we do in simulation is just take the total number,
yeah,
and don't worry about partial molar volume for the initial calculation.
Yeah.
But if we want to do those calculations, there are ways of doing it later on.
Yeah.
So we will just find the total density and mix them in proportions,
yeah,
and make sure that it is close to experimental density and proceed.
Yeah.
Okay. So although there were separate PDB files, Now there is only one GRO
one
file.
GRO file which will contain the
Information
way
of both.
you have given in PACMOL INP file. Suppose in INP file first there is methanol PDB and then there is water PDB. So in GRO file you will have first methanol
Right.
coordinates 431 and then you will have water coordinates 431. So
Okay.
the sequence you give in PACMOL's INP file will be reflected in the GRO file. It will have the same sequence.
So now we have to go to the top file.
Yeah, now we'll
Will
have
there
to
be two top files or one top file?
one
Finally.
top file, but there will be two ITP file.
Why is that?
Because water and methanol molecules are different. In top file, you just have to write sigma, epsilon and charge.
So you will write for all of them. All
You can
sides.
write for all of them. First you
Okay.
can write for methanol and then you have to write for water because you have to maintain the same sequence throughout.
Okay.
Right. So now I'll go to the top file. So this is the top file. Right. So NB function is the non-bonded function, 1261 potential. Combination rule 3 I have already said earlier. So here you see that first there is OPLS underscore 002, then 007, then 004. This is for methanol.
Okay.
Since for methanol we are taking OPLS force field. So the first one is for methanol and OPLS underscore 002 is for oxygen. So the mass is given there. Then 007 is for methyl group since we have taken united atom. And then OPLS underscore 004 is hydrogen atom.
So your second column are the masses, the third column is the charge.
Yeah.
And what is that P type AAA?
Explain the data mouse is easier.
Mouse? Okay. So, yeah, so this is,
Just move it a little, yeah.
yeah. So this is charge, this is charge on oxygen atom, this is on methyl group
Okay.
and this is on hydrogen atom. This is P type is, this is atom type.
Okay.
A is for atom.
Okay.
Then this is sigma in nanometer and this is epsilon in kilojoules per mole. And this is for water molecule.
Okay.
This is oxygen and 2 hydrogen.
Okay.
So this is the mass of oxygen and hydrogen. This is the charges on each of the atom. This is again atom type and this is sigma and epsilon values.
So that whatever OPLS minus 002 underscore 002,
Yeah.
it is given by the system or?
No. You have to include it because see, you have to have the charge of oxygen, methyl group and hydrogen atom, right?
Correct.
You have to get it from somewhere. You cannot
Correct.
put some random values of sigma and epsilon. So what you do is you go to the top folder which you will get when you install Gromacs,
Right.
and then inside the top folder you will have OPLS folder.
Okay.
Right.
So you have got the first 3 lines for methanol from the OPLS folder.
Yeah, from OPLS you will have ff non-bonded.itp and then there you have to go search for methanol oxygen atom charge and oxygen atom methyl groups charge and hydrogen atoms charge, and from there you will get sigma and epsilon values.
Okay.
And then you have to include ITP file for methanol and water. So this here also you have to maintain the same sequence. First you have to write for methanol and then you have to write for water.
So for the P type you have given AAA.
Yeah.
Can you give BBB?
No, it is only A type allowed, and if you give residue then you have to write
RES.
R.
R only.
Yeah.
Okay, so either it's a or an R there.
Yeah.
Okay,
And then you have to include the ITP file for methanol first, since in PDB file we have methanol first and then water. So methanol first and then water, and then you have to define your system. You can write anything in there, and then you have to write molecules you have to define. First is MEO.
No, before we do that, when after the 2 includes you have 2 blank lines. Do you
Yeah,
need
you
those blank lines?
can. You cannot give the you don't require the blank line as well, but just to get a clear picture.
So after the system,
Yeah.
there is something NaCl. What is that?
That is to define the system. You can write anything. You can write 50% water methanol mixture. Anything you can write. It
But-
doesn't count.
Okay, that is just a
To
anything.
define a system,
Okay.
you're just defining your system.
Okay.
And then you'll have molecules type.
Right.
So here you will have to give the residue name of the molecule. So
Okay.
since we have MEO in the first, so we'll have MEO as the residue name, then
Okay.
the total number, that is 431, and then SOL, that is solvent, that is
Okay.
431.
Right. Okay.
So this is the topology file. Right. So this I have already told that it will generate 1,4 interaction, and then fudge LJ and fudge QQ are for LJ 1,4 interactions and for electrostatic interactions.
Okay.
And now we'll proceed, now since we have GRO file, we have topology file, so we'll proceed towards the energy minimization of the mixture. We'll use the same command and we'll use the same em.mdp file. So we'll first generate the TPR file using the command grompp. So we'll combine MDP,
So from
GRO.
now onwards there will be only one file now, not two, because we have already combined everything into.
Yeah, into one file.
Okay.
So we'll use the TPR file because in em.mdp file is same.
Okay.
In conep.gro we have all methanol and water molecules coordinate. In topol.top I have already included water and methanol's ITP file, and it already contains information like sigma, epsilon charge of both water and methanol molecule. So I don't have to include different file for water and methanol.
Okay.
And now I will generate em.tpr file, which will be my input for md run for energy minimization. So I'll just type the command md run space -v space -deff_nm space em, which will generate all my full file output file, which will have initial as em.
So now what we are doing, calling everything by EM.
Yeah,
So which means in each directory there will be several EM files.
yeah,
Okay, so it is very important to keep the directory structure intact,
yeah.
because if any mistake is there, everything will be gone.
Yeah.
Okay.
Because we are performing in separate directories, right?
Okay.
So in water we'll have water ka EM, in mixture we'll have mixture EM.
Okay.
So directories have to be different,
Okay.
right? So after the energy minimization, we'll have something like this displayed on screen, where we see potential energy is negative, maximum force and normal of force is found to be there.
So this time also it has taken 22 steps.
Yeah, it
Last time
depends.
also 22.
It depends on the system also.
Okay.
If we have a large system, it's just 4. See, because the total number of molecule here is 862. In
Correct.
case of water, we have taken 899.
Okay. So it's very close.
It's very close. So if you have a large system, suppose 4000 molecule, then it will take
Maybe longer.
longer time or longer step.
So now instead of writing something after 22 steps,
Yeah.
can I write that force every step,
Yeah, it is displayed on the screen. Force on each step is
Okay.
displayed on screen.
or is that also written into a log file?
Yeah, em.log file will be generated.
So-
You will have force as a function of time and as a function of step.
So whatever is happening every step, that is written
Yeah,
in a
yeah,
log
yeah,
file.
yeah, definitely.
So is there a log file for every execution?
Yeah, there is a log file for every execution. For energy minimization, you will have em.log.
Okay.
Then when you do full molecular dynamics simulation, you will have full.log.
Okay. And many of these things in the log file also will be on the screen if you are doing on the screen.
Yeah, sure.
Okay. So now again the maximum force is of the order of 10 to the power 2 on atom 2497.
2497.
Okay.
So now since we have energy minimized configuration, we have the topology file and we have the full.mdp file. So we'll proceed towards the molecular dynamic simulation of the mixture. So here also we'll combine the MDP, em.gro and topol.top file to a TPR file, which will be my input for MD run using the command grompp.
So em.gro is the result of your
Energy minimization. So we'll,
that is a one file.
yeah, that is one file.
Okay. Consists of all the coordinates.
All coordinates of methanol and water. This is the energy minimized configuration.
Right.
And we will use full.mdp, which contain detailed information about algorithms, like which is the algorithm we are using for keeping the velocity, temperature constant, for pressure constant, and how many
that
steps we want to.
MDP
Yeah,
that we are using here, is it the same that we use for water?
yeah, you can use the same MDP file.
Okay.
I'll also show the details of the MDP file when we actually run the simulation in
No,
lab.
but that MDP file here, should
Yeah.
it not contain parameters for methanol as well as for water?
No. For water and methanol, we don't need different parameters. What is in the MDP file is the number of steps.
Okay.
It is the time steps. Then
Okay.
after how many steps you want to save your coordinates, velocity, force, trajectory,
So the
and
MDP
then
file,
cutoff.
so it has nothing to do with the types of molecules.
No, it has nothing-
just has a global information of the system.
Systems.
Okay.
Yeah.
And the GRO file will have only the coordinates.
Yeah, GRO file will
Mainly.
have
And the
only
box
the
length.
coordinate and box length. Yeah.
And your topol.top will have all the parameters.
All the parameters, charge, mass, sigma,
Okay.
epsilon.
And that connectivity, that is also in topol.top?
Yeah, that is in topol.top. That
Okay.
is ITP file is included there.
In the top, okay.
In the ITP file it's there.
So your full dot TPR will be the output of this?
Grow MPP command, and it will contain all the information which is contained in the MDP file,
Okay.
GRO file and top file.
Okay.
And so now we will use this TPR file for MD run. So we will type MD run space minus V space minus DEFFNM space full. So all my output file generated will have initial as full. So full dot GRO, full dot XTC.
Right.
So like this. So now since we are done with the simulation, so something like this will be displayed after running the simulation.
So does this display include the number of steps or
No, 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 it doesn't include the number of steps.
So that will be in the log file.
That will be in the log file.
Okay.
Your temperature, pressure at each and every time step, that will be contained in the log file itself.
Okay.
That will be full dot log. So now we will proceed towards the analysis of the trajectory. So here also we will go first creating an index file. So to create an index file, we will first type the command make underscore ndx minus c space em.gro. Similarly here we can use any gro file. We can use full.gro or we can use conf.gro. Then space minus o is the output file name.
So
Then
all those GRO files will have the same index.
same index, yeah.
Okay.
And then minus o space index.ndx, and then when we type enter, something like this will be displayed. So here we see there are 5 default index group that is already created. So the first default group is system, that will contain a total number of 2586 atom. It will contain all methanol and water molecule. Then there
so
is
the index is index of all the atoms.
all the atoms.
Okay.
Yeah. Then there is other. Other will contain the index file of all methanol.
Okay.
Then MEO,
But if you had given water first and then methanol, the other would contain water first?
no, in case of water we have water and sol. It will have
No,
water.
because in the data
Yeah.
you had given methanol first, no?
Yeah.
So the output, that index file output is the same for all
Yeah,
systems?
it is the same. Like it will have one system, then it
Okay.
will have two for like it would have 2 for methanol, right? One is
Okay.
system,
Right.
sorry, one is other and one is MEO. Since
Okay.
MEO is the residue name that we are giving.
Okay.
Then there is 2 for water,
Okay.
water and sol. Then there is non-water. Non-water is also methanol. So
Okay.
these are by default created index file. We cannot change this. It is created by default by the system.
So every time you do that make index, it will create that file.
It will create that file depending on the molecules or system that you are
Suppose
simulating.
I had given only water,
Only water, then it would have system,
right?
water and SOL. SOL is a residue name.
Okay.
So it would have 3 index file.
So if you have 3 solvents, you will have
Maybe 9 or 10
Okay.
or maybe more than that.
But there we have no choice.
There we have no choice. We cannot change it. We cannot edit it.
So that is a
It
system
the
output.
that is a system output. It is created by default.
So now to make indices for all your atoms, you have to give that A.
Yeah.
Right.
So now since there in water we have 3 sides and 2 hydrogen sides are equal.
Okay.
So we'll just create 2 for water, and in methanol we are using united atom for the methyl group
And oxygen?
oxygen and hydrogen.
They are
So
different, so you will have 3.
3 for methanol and 2 for water.
Water. Okay.
So we'll first type A space OW, then
Okay.
enter.
So this is before that Q comes.
Yeah, this is before that Q comes.
Okay.
Then we'll type A HW1.
Okay.
This is for water, and then for methanol we'll type A space O1.
Okay.
Then A space Me2 for methyl group.
Okay.
Then A space H3 for hydrogen, and then finally to save it we'll type Q.
So now that HW1
Yeah.
is just the name you are giving. It could be HW2.
Yeah, it could be HW2, but it has to be HW1 or HW2 for
Okay.
water.
Okay.
Similarly for methanol, since in the PDB file it is already O1, Me2 and H3, so we have no choice. We have to give O1, we have to give Me2 and we have to give H3.
Okay.
We cannot write H4 or H1 or H2.
So now is the order of these commands important?
No, it's not important.
So I can do AH3 first and then AME2.
Yeah.
Then AOW, I can mix them also.
Yeah, you can mix them also.
Basically,
The
I have
order
to give 5 commands
to
to
generate
generate indices
index
for
file.
these 5.
Yeah.
So what is the output file of AAW?
Yeah, so when you type all this,
Yeah.
you will get like this. So there is like there is
Okay.
already 5 default index file created. So
Correct.
the 6th one will be for OW. So
Okay.
6 OW, there is 431 atoms, right?
Okay.
Then 7th is for HW1, that is 431 atom. Then 8th is for O1 of methanol, again 431. Then 9th is for methyl group of methanol, 431 atoms. And then 10th will be H3 of methanol, that is also 431 atom. So when you open the file using the command vi index.ndx, you will see all the index file, like first will be 0, like it will contain system,
Okay.
and then there will be 1 to 2, 5, 8, 6 atoms.
Okay.
Then when you go to OW, it will have 1 to 431 atoms.
So whatever was in your default file that you showed,
Yeah.
plus these will be in your
Index file, yeah.
Okay.
So now we have index file, we have XTC file, and we have TPR file,
Okay.
right? So now we will use all these 3 files to create to calculate radial distribution function and diffusion coefficient.
You have a printout of that index file total?
Yeah, we can show it in
Okay.
the next
Right.
lecture maybe.
Okay, fine.
So now to calculate radial distribution function between
But just as your PDB file
Yeah,
or your topology file,
Yeah.
you can create it by yourself typing all those things. You can
like
actually type on the screen.
yeah,
na?
but yeah,
It may take time.
it will take long
The
time.
same way, if I know what my system is, can I create that index file? Since I know all the atoms, all the molecules, can I create that index file by hand?
Yeah, you can create it by hand, but it will take long time, because you have to specify each and every atom number is to be written there. So if you have more than
No, but you said that the index file will have 10 lines.
no, it won't have 10
Oh,
lines.
it will have an index for every atom.
Yeah, it will have an index for every atom.
Okay.
So to now coming back to radial distribution function, so we are calculating between oxygen site of water and oxygen of methanol. So we'll use the same command g_rdf, and XTC, TPR and index file are the input to calculate radial distribution function
This is exactly like the same
for
as
water.
the commands earlier.
Yeah,
Okay.
and then -o space whatever the output file you want to give.
Okay.
So I have given here OW for water and OMEOH rdf.xvg,
Okay.
and then it will ask you to select a group.
Okay.
So here you have to select 2 groups, right? So first you will select oxygen of water, it is in group 6,
Okay,
right?
right.
And then oxygen of methanol is in group 8.
Okay.
So first you type 6 and then you type 8, then it will create an RDF file, like rdf.xvg file.
But when you type that first line
Yeah.
written in red, does it prompt you to type a particular group?
Yeah, it prompts you to type a
So
particular
type group 1,
Yeah,
type
yeah,
group 2,
yeah.
it will give you that.
Yeah.
Okay.
You see here it's written select a reference group and one group.
Okay.
So around which atom you want to
Correct.
know the density
So
of.
first you select a reference group,
Yeah,
then
yeah,
second time one more group.
Yeah.
Okay.
So after that you will have a file OWOMEOH rdf.xvg. You can view the file using the command xmgrace.
Okay.
So just type xmgrace space the file name, and then it will show the graph as this.
Okay. So,
this
for O water, OMEOH, you have 6 and 8.
8, yeah.
Okay.
And now for hydrogen of water and hydrogen of methanol, we use the same command, just
Okay.
give the file output file name different, and then here what we do, since hydrogen of water is required, so hydrogen of water is in group 7, right?
Okay.
So you type 7 first and then type 10 later, because 10 is hydrogen of methanol, and then you will have the file O hydrogen water hydrogen methanol rdf.xvg. You can plot it using the same command xmgrace.
Yeah.
So it will show something like
so
this.
basically you can choose any pair
Yeah.
and get all the distribution
Yeah.
functions.
So there.
You can also get H water also.
Yeah, H water,
So you give the same index?
Yeah, for H water you have to give. It's like water is in group 7, right? So
Correct.
you have to type 7 twice
Okay.
for getting GFR
Right,
between water of hydrogen of water molecule.
Okay.
So now we'll go to diffusion coefficient of water and methanol. So we'll use G_MSD, same XTC, TPR
Right.
and index file is required, and -O MSD water, since I'll first calculate the diffusion of water molecule. So this is the output file name,
So
and it will.
is there some way
Yeah.
where I can include all those files in one command, -F full dot xtc minus s full dot, every time you have to type all that, no?
Yeah, every time you have to type all
Is there
that.
a way to put that on in some shortcut?
No, there is no
Huh?
shortcut way.
Or can I not create a shell script for that?
You can create
In
a
principle,
yeah, you can
right?
create that.
So that shell script you will give input, then
Yeah.
you will only need that output as the msd water dot
XVG.
That is the only thing that is changing.
Yeah.
All the rest are the same.
Yeah.
So there must be some ways.
Yeah, you can write a script file as well, so you don't
Okay.
have to type it again and again.
Correct. Okay.
Right? And it will also ask to select a group for
Diffusion.
diffusion. So here we have to calculate diffusion for the whole molecule.
Okay.
Right? So for if you want to calculate for water, so what we do here is, yeah.
You have to select that group, no?
Yeah, we have to select a group. So you see in group 4 there is water and sol.
Okay.
Water is in 4 and sol is in 5. So you can type either 4 or 5.
Okay.
It will display the diffusion coefficient as shown in the screen. And to plot it, you just have to type xmgray space your file name dot xvg.
So now to calculate the diffusion coefficient of hydrogen, you can give that site also?
Yeah, but there is no meaning of calculating diffusion of different sites. Like the molecule will diffuse as a whole.
I understand. So whether you do for O or H, they should both diffuse with the same diffusion constant.
Yeah, they should in
But
principle.
so how does the system decide that oxygen is the main atom, or that is built into the system?
That is built in because oxygen is the center of the molecule.
Okay. So for oxygen it will be for water, and similarly for methanol also?
Yeah, for methanol also, like we'll use the same command,
Right.
just we'll give the name of the output file different. And then for methanol we type, we just have to see methanol is in group 2, right?
Okay.
So we just type group 2,
Okay.
like we type 2 and then we'll get the value of diffusion coefficient on the screen.
Okay.
And we'll have the output file as xvg, and to plot it we just type xmgrace output file name dot xvg.
Okay. So now we have completed a calculation for a mixture.
Yeah.
So we have done all the file structure, all the commands, these are all done. From next time we will actually do the practical part, right from installation to execution of all these things what we have studied so far. We will close here and see you next time. Thank you.